Okay, let's see if that works. So I have a connected graph of order 8, and it contains two C4s. They have no vertices in common. Okay, so I mean, what I'm gonna, you can draw it however you want, but so I'm gonna draw a picture and then I'm gonna write some words. Let's say A and B. Let A and B be two C4s in the graph. With vertices x1, x2, x3, x4, and y1, y2, y3, and y4. Okay. All right. What is the least possible value for, what is the least possible value for the number of edges? Why isn't the answer 8? Okay, does everybody see you gotta have at least 8 edges? Okay. What's the one condition that I'm missing from? It's not connected. Okay, so what's the minimum number of edges that I need to make this a connected graph? It's a disconnected graph at this point. One more edge. Okay, so since the graph wasn't connected, we need at least one more edge. And here is a connected graph with 9 edges. And if you want to be really over the top, with 9 edges and 2 disjoint C4s. Okay? So it depends on how many words. I understand that we have done a lot of graph theory this semester with pictures. And pictures are nice. Do you want your homework? Help me out. So we've done a lot of things. We've looked at a lot of graphs, and and maybe my fault. I've waved my hands, but now it's time that we have to get into the sort of practice of being concise with what we're trying to show. Okay, so one more time, we know that we have to have at least 8 edges because we have 2 disjoint C4s. To make the graph, to be sure that the graph is connected, we need at least one more edge between the cycle C4, the cycle A and the cycle B. One more edge makes the graph connected. So 9 is the minimum number of edges. So here's a connected graph with 9 edges, and that's the smallest possible. Okay. Assume that G contains no cut vertex. Let's look at it now. Does it contain a cut vertex?
Yes.
What is a cut vertex? Okay, so how many cut vertices? Does this graph have now? 2, x4 and y4. If I remove either of those vertices, the resulting graph is disconnected. So there are 2 cut vertices. So now assume that G contains what is the least possible value, and we still have 2 C4s, and we want the graph to be connected. What's the smallest number of edges so that I can have 2 disjoint C4s and no cut vertex? since there are cut vertices at this point, and by the way, I want to note that if once I have the C4, A is a C4 and B is a C4, it doesn't matter which edge I put in there. Okay, they're isomorphic. It doesn't matter whether I put X4, Y4 or X4, Y2 or X1, Y3. As long as I put an edge from this C4 to that C4, the resulting graph is connected. And the resulting graph has two cut vertices. Okay? How can I remove those, how can I eliminate those cut vertices? Adding an edge. Adding any edge? Adding any edge?
I'd say so.
You say so?
You can't make incidents of that.
So you think, so Ben, what about that edge?
No. You can connect it with X4 or Y2.
Okay, so if I add this edge in, what's wrong with that edge?
It's incident to what was already a.
Okay, it's incident to X4, and X4 is still a cut vertex. We want to add edges so I have no cut vertices. So adding an edge to X4, or in this case Y2, would be a problem. So we must add at least one more edge, and it can't have an end vertex of X4 or Y2. So which one do you want to add?
We'll do X1 to, I can't really see.
X1 to Y1.
Sure.
Maybe you should move up a little. Okay. Okay. So assume that G contains no cut vertices. We know we need more than 9 edges. Here is a graph with 10 edges. So this is the minimum number of edges in a 8-vertex graph that has 2 C4s and no cut vertices. Okay, I. Assume G contains no odd vertices. What's an odd vertex?
Vertex with degrees of odd number.
Okay, so no vertices of odd with whose degree is odd. So I'm gonna continue down the list. So I'm going to assume that we want a graph that has no cut vertices, and it has no odd. So given 2 or II, we now want to do 3. II. Assume G contains no odd vertices. What is the least possible value? There's 2 ways to look at this. We could have gone back to, by the way, we could have gone back to just the original assumption of 2 C4s and not put in the conditions from I and II. But I think they want us to think, to look at this as not, to include the requirement of I and II. So I want a graph, order 8, 2 C4s, and I have no cut vertices, no odd cycles, no odd vertices. So what do I need to, how many odd vertices do I have here? By the way, when I put this second edge in, it's clear that I don't have a cut vertex. Is that right? Okay. Okay, and it's important, of course, that X4 couldn't go to Y1. It has to be an edge that's parallel to X1, Y1. Okay, so I have, how many odd vertices do I have at this point? What is an odd vertex? Okay, so odd degree. Okay, odd degree. So what do I want to do? I see 4 odd vertices. In this case, X1, Y1, Y2, and X4. So can you give me a way to get, how can I get rid of those odd vertices?
Draw edges between the odd vertices, but make sure that two odd vertices have the edge between them.
Okay, so, and I don't want this to be a multi-graph. This is important. I want this to be a graph. It's asking for a graph, a connected graph. So I don't want to add the edge y2, x4. It's an x. I don't want to add the edge y2, x4, because that would make a multi-graph. So if I add, let me do it in a different color, maybe. So if I add the edge y2, x1 and x4, y1, then the degrees are 2, 2, 2, 2, 4, 4, 4, 4. And this is the smallest number that meets condition I, 2 i's, and 3 i's. Okay, assume that G contains no even vertices. What is the least possible value for E of G? So I'm gonna, we can just keep on throwing edges in here. So at this point, I have all the vertices are, this is a degree 4 vertex, 4, 4, 4, 2, 2, 2, 2. How many more edges? So I have 8 even vertices. And I'm going to read this as we're building on I through IV. So how many more edges? I have 8 even vertices, and I want no even vertices.
If we're building on this, part 3 says no odd vertices, and now we're saying no even vertices.
Well, so
just
given
building on
the
1 and
graph
2.
from 3, okay, so we're building the graph as we got.
Oh, I see what
Okay,
you're
so
saying.
now I'm going to take
see
that
what you're
graph. Now I want to take that graph and make it have no odd vertices, no even vertices. So what should I do? X. Okay, so I can try another color, one more color, hopefully black. X3, Y3, X2, Y2. Now I can't put in X4, Y4, and X1, Y1. So if I put in X, what am I going to do? So we have to do this carefully. That's gone. So I'll add this edge and this edge and, wrong again. So you have to come up with a way to come up with this. So let's see, I'll put in this edge. Let's see which ones are, so, yeah, so this is now, it becomes a little bit more difficult. So one more time. I'm going to go back to where I was. I'm hoping. So I'm getting all the black edges out of there. And at this point, what do we have? We have vertex of degree 4, 4, 2, 2, 4. Wait, do I want a 4? Is this black edge in here?
No black edges.
The blue ones.
Oh, the blue one is, okay. Okay, so this is 4, 2, 2, 4, and this is 4, 4, 2, 2. And you know, so now you have to explore a little bit.
So we don't need the blue pad.
So, well, these blue paths, we put these 2 blue edges in from a previous part.
So we last need to create in base graph.
Okay, so we need to do it where?
Based on this graph,
Based on this graph, yes.
right?
So we can connect the x1 with the y4.
Okay, x1 with y4, okay, and then
And x4 with y2.
x4 with y2.
Yes.
Okay, wait a second, x1 with y2 and x4 with y2?
X4, well, if we connect x1 with y2, we can connect x4 with y4.
y4, okay.
Oh, so that's y4, so y1, yeah.
Y, oh yeah, let's see, this
Not
was y1,
y4.
y1, y2, y3, yeah, they've been erased. So y1, y2, y3, and y4.
Yeah, we just need to connect the x1 and x4 with the y3 and y4.
Mm-hmm. Okay, so one, you can, and the important thing is, you know, we're free to do almost anything we want. So, let me just go, the easiest way I would see how to do it would be, so, I mean, you know, you have the flexibility, there's 8 vertices, you can put edges wherever you want. Okay, so now what do I have? I have all vertices of, and this edge is here. This is a degree 5, this is degree 3, 3, 5, 5, 3, 3, 5.
Well, but on this supposed to be the C4, so, oh, this.
We still have C4s.
Yeah, yeah.
The C4s are still there.
Yeah, it's C4.
Yeah, and it doesn't say contains 2 C4s, it doesn't say it contains only 2 C4s.
Okay.
Okay? Questions? And again, one of the reasons that you want to be looking at problems like that is you just need to spend time looking at graphs and how degrees relate to each other and how edges can change the structure of the graph. Questions about that? Okay, should we move on to 89? Number 10. Okay, so this is a degree sequence problem. So D1, D2, Dn is a graphic sequence. Now, remind me what that means. So I can find a graph that has exactly the degrees D1, D2, Dn. So how many vertices are in that graph? N. Okay. So let that be a graphic. So my proof is going to be let G be a graph of order n. How do I know it's got order n? Because I've got n degrees. So with degree sequence, D1, D2, Dn. Okay, and just for completeness, let Vi be, let the degree of Vi equal Di for I equal to 1, 2, up to n. Okay? So now, what do I need to do? I need to show that for each k, the sequence d1 plus k, d2 plus k, up to dn plus k, plus n plus k minus 1, n plus k minus 1, n plus, so there's k so how many vertices in this new graph? So construct a new graph. Of order, how big?
N plus k?
So I've got n vertices from the original graph, and then I got k more. Right? This sequence, d1 plus k, d2 plus k, dn plus k, n plus k minus 1, n plus k minus 1, and so forth, that has n plus k vertices in it. That sequence has n plus k. Okay, so for each the sequence is also I don't permutation of a graph is a graphic sequence. The permutation did the word permutation bother you? Okay, so it's just some ordering. I don't know. Usually we list the degrees in ascending or descending order. We don't know what order they're in. Okay. Okay, so I'm going to construct a new graph. Here's G. That's G. And here are the vertices. Let's put V1, V2 to Vn with degrees D1, D2 down to Dn. Well, what's the total number of vertices that I need in this graph? How many more vertices? Look at the sequence. I got D1 plus K, D2 plus K, Dn plus K, and then I got how many, let me be bold, how many n plus K minus 1s are there?
Okay.
K of them. So how many more vertices do I have?
Okay.
K vertices. So here are K more vertices. So if at this point, here's my graph, here's my intermediary graph, I'm building graph H. If I stop now, what's the degree sequence of this graph?
So what's the degree of this K point?
At this point, nothing. 0. So I mean, they're just isolated. I haven't put any edges in.
Okay.
So what's the degree sequence of H now?
The same with 4.
Okay, D1 through Dn,
It's still the.
but we have to add these.
And the K0.
And K zeros. I know that's like, I mean, at this point, so just for our own notes, our degree sequence is D1, D2, Dn, 0, 0, 0, 0, K times. Okay, so let me just remind you, it's good because at this point I know that I have n plus K points. And why is that good? Because this degree sequence that I want to end up with has the first n plus K more points. Okay? All right, so let's look at these numbers. I mean, if you had to guess, and you're going to put D1, I need to get D1 up to D1 plus K. So I'm looking for, I'm constructing, I'm trying to, so this is notes to us. D1 plus K, D2 plus K, Dn plus K, and then what's n plus K minus 1, n plus K minus 1, n plus K minus 1. How many of these? I have K of these. That's what I'm aiming for. I'm not there, right? I have D1, D2, Dn, and a bunch of zeros. So, I mean, you got to try something. And I'm going to look at this for a second, and I'm going to go, oh, that's kind of interesting. N plus K minus 1. N plus K minus 1. And you can almost, from that, you can almost say, what are those last K vertices? What's their adjacencies going to look like?
Complete.
Complete. What do you mean complete?
K has to be a complete graph.
Yeah, but more than that, how many vertices, let me start again. How many vertices, D1, D2, Dn up to, D1, D2 up to Dn, and then K zeros? How many vertices are in this graph so far? How many? N plus K. What's the largest, this is a graph. What's the largest degree you can have? Let me What's the largest degree you can have in a graph of order m?
M minus one.
M minus 1. Here I have a graph with, what's the order of this graph?
M plus K.
M plus k. So the largest degree I can have is
N plus K minus
n plus k minus 1. And the only way to have n plus k minus 1 is to
put with everything else.
put them. So that means, that notation means put it adjacent to everything. Okay, so let me stop at this point. The degree of this point is what?
K plus N minus 1.
At this point is n plus k minus 1. The degree of, let me put in another point just for symbolism. Let's put a point there. What's the degree of this point right now?
1.
1. And this point?
1.
And all of these points?
1.
And these points?
N plus 1.
N plus 1?
Yes. D N plus 1.
Sorry. So it's d, this, so if I choose a point right here, di, the degree of di is now di plus 1.
Yes.
Okay. I need more. What do you think I should do?
Compile the B's to all the K's.
Okay, so continue. Okay, so this is, consider this graph. This, I'm putting quotes around it, this graph. Is it clear what this graph is? And just to make it a little bit clearer, so here's the original graph. Did we give it a name? We did not. No, that's, yeah, G. And here is a case of K, and I'm putting all these edges in here. Okay, so here's a new graph. My vertex set is the set of vertices of G and these K vertices. And my degrees are, let's see, what's the degree of a vertex here?
N plus K minus
Oh, yeah, okay. Yeah, I put this is a complete graph. I guess I went one step too far, but okay. So this is a complete graph. So it's adjacent to everybody here and everybody over here. So it's adjacent to, let's see, we got originally n, and then k minus 1. So I've got each of these vertices have degree n plus k minus 1. And the next vertex, of course, has the same degree. N plus k minus 1. N plus k minus 1. What's the degrees of these vertices? And let's order these. This originally had degree d1. This originally had degree d2. This originally had degree dn. Now, and that graph, of course, is still there. Now what's its degree? d1 plus k, d2 plus k, dn plus k. Okay, is that clear? Is that clear? Does that make it clear? So show that for each k, and I chose k arbitrarily, the sequence these down to dn plus k through n plus k minus 1 is a permutation, and forget the word permutation, it's a graphic sequence. It's a graphic sequence because there's a graph that attains this sequence. Questions? Okay, what's next? Okay, recall that, is it page 90, number 2? Page 90, number 2? Okay. Recall that C of G denotes the number of components of a graph. show that the edges of G is less than or equal to the components of E minus G is less, sorry, put your glasses on. Show that the number of components can only go up and can only go up by 1. What does that mean? And what's important is, so here is G. G has C components. I'm going to remove one edge. So between any one of these components, how many edges are between this component and this component? Okay, so I certainly can't be removing an edge between these two, or these two. So in fact, the only place I can remove an edge is let C be some component of G. So what does it look, what happens, how can the number of components go up? The number of components increases when? I'm going to remove an edge. So consider C minus an edge. I'm going to take some component and I'm going to remove an edge. Do the number of components have to go up? Mm-mm. So if I remove an edge from some component, then the number of components increases by 0, 1. So by at most 1. So now that's what you need to prove. Okay, so take a connected graph and remove an edge. Can C is a connected graph, minus E have more than 2 components? Question mark. So I have to prove this. I have to prove that if I have a connected graph and I remove an edge, then I can't get more than 2 components. In fact, I may not even get 2 components. Okay, is that clear? So how would I prove that? Yeah, come on, it's your favorite proof technique from Math 3000. If you haven't taken Math 3000, then it's a proof technique that you used in calculus and probably linear algebra and any other math course. We're going to prove this by contradiction. Okay? What do I mean by contradiction? So let C be a connected graph. What assumption should I be contradicting? Come on, help me out a little bit.
Either so it'd be the opposite of one direction, so either C minus E has less components, or C minus E has 2 more components.
Okay, so is it possible that C minus E has fewer components than C? And C doesn't stand for cycle now. C stands for component. Is that possible? suppose that was the case. Well, C has only one component. C has only one component. So when I remove an edge from C, an edge from C, we can't end up with 0 components. Is that clear? Okay. So that's pretty easy. So the other possibility is that C minus E has, we took care of fewer. C minus E has more than. Okay, C minus E has more than C, than the number in C, the number of components in C.
By 2.
Okay, well, let's start with, we'll get to that. Okay, the possibility, we're removing an edge, and the possibility of the number of components goes down, that doesn't happen, or the number of components goes up. And now what I want to show is if it goes up, or stays the same. If it stays the same, we're done. Or the number of components goes up, then it can only go up by 1. Okay? So let's suppose the number of components increases by more than 1. So I remove an edge. C minus E has at least 2 more components than C. So, and I'm going to look at a picture. Here's C. Here's an edge. And now what we have is that I now have this many components. At least. Maybe it went up by more than. So what's wrong with that? Where can the edge lie? I've removed one edge. So what are the possibilities of where that edge lies in the graph? When I say lies, we got at least 3 bodies. So tell me where the edge E could have originally been. Do you want me to label those components? Anybody?
It has to be within one.
It's either that edge is in one of the was in one of the components. Well, if the edge was in one of the components, then the original graph C would have been disconnected. Okay, so one more time. The edge is either in one of the components or between how many of the components? 2 of the components. Okay. And I'm assuming that I already have 3 components or more. So one more time. The edge is either in one of the components. So one possibility is that's where E was. If E is in one of the components, then the original graph was disconnected, and that is contrary to having a component. Or the edge, and again I have at least 3 components, the edge lies between 2 of the components. Okay, so this is the edge E. We removed it. It lies in one of the components of the disconnected graph, or it lies in between 2 of the components. But if that was the case, then the graph originally, what does the graph now look? What does the graph look? What can you tell me about this graph?
Disjoint.
It's what?
Disjoint.
It's this something.
Joint?
Disconnected.
Oh.
Right, or not connected, but disjoint is. We'll get to some other things that are joint.
Oh, okay.
Okay? But it started out as a connected graph, so a contradiction. Is that clear? I know that this is a pretty simple proof, but it's worth suffering through some of the details to actually see how to prove. Results in graph theory sometimes are a little difficult to get all the details and be sure you're dealing with all the cases. Questions? Okay, the Cartesian product. Any questions on the Cartesian? Was that number 90, page 93, number 12? I mean, you know, so one of the things about, you know, you can draw them however you want. One of the reasons we come up with these strange things, products like this, is we want to increase our dictionary of graphs. So looking at this Cartesian product, we're able to take two graphs and construct some, and there's actually many different products that you can look at. Okay, the Cartesian product is just one, but there are many others. There's a lexicographic product, there's other products that give you different graphs. And sometimes those graphs have nice structure that you want to deal with. Okay? So let me ask, I think for this problem, I don't think there were many questions on this problem. Any questions from number 12 on page 93? Because I really want to get to number 21. Even though we talked about number 21, I want to go through the details one more time. How would I write it up?
Can you just look at part C? I'm not sure I was thinking of.
Okay, find the relation among the degrees. So is that degree or distance? What is DUV? Find a relation among the degrees in G. I see. Okay, so the vertices, that's the degree of UV. So what's the relationship? Got it. So what's the relationship between the degree of a vertex? So I have an X is in G and Y is in H. Okay, so I'm gonna sketch out what this might look like. I have each of these are a copy of G. This is a copy of G. This is a copy of G. This is a copy of G. Okay, and now I'm going to look at this is a point X in this copy of G. This is the same vertex in this copy of G, and this is the same vertex in this copy of G. And this product, what am I going to do? On these vertices, what are you going to do? Well, okay, so I'm going to put a copy of H. Okay. So okay, find the relation among the degrees, the degree UV in G square H, and the degree of U in G, and the degree of V in H. So I might think of this as vertically, this vertex X corresponds to a vertex in G. In G, what's the degree of this vertex in G?
N, I don't know.
Okay, D.
D.
Okay, so let's say this is degree in G of X is the degree in here. Okay. What's its degree in H? Okay, so let's label the vertices in H. V1, V2, V. How big is H? It doesn't say. Doesn't say. However big as H is K vertices. So in this red shape here, this vertex looks like looks like one vertex in H. It looks like the vertex V1 in H. So the vertex across in blue, the degree of that vertex is going to be the degree of V1 in H. Is that clear? I mean, you can think of it as perpendicular. Up and down, the degree of X in this copy of G is the degree in G of X. Across, the degree of V, in this case V1, in H. So the degree in the whole graph is going to be the degree in G of X plus the degree in H of, I'll call it X, but, okay. So you add the degrees up. And of course, you've looked at some of these already, right? So just, did you look at C4 cross C4? Did I make that up? Okay, so if I'm looking at C4 cross C4, let's look at C4 cross P4 just to be different. C4 cross box P4. So here are 4 copies of C4. On these 4, these are the same 4 vertices. What am I going to have on those 4 vertices? A P4. Now you have to be consistent. So if our P4 looks like U1, U2, U3, U3, and U4, then there has to be consistent. This is the U1th copy, this is the U2th copy, this is the U3th copy, and this is the U4th copy of C4. Now, what happens in this oval? What does the graph look like in this oval across these? So this is a P4. Does this vertex go to any vertex down here? Does this vertex go to a vertex here? Jason, any other vertex? So what's the degree of this vertex? It's the degree in G plus the degree in H. Okay. Okay. Other questions? And again, it's a way to come up with, you know, I've heard students tell me, I just ran out of graphs. Trust me, you didn't run out of graphs. But this is a way to construct some interesting graphs. It's a way to construct some graphs that are sort of have some nice symmetry. Okay? And they, as you'll see, they may come in handy as we move on in the semester. Okay, the last one I want to go through in detail and talk about this, where we ended the other day. So let G be a graph of order at least 5. Show that either G contains a P3 or G complement contains a C3. So just because we need to be clear on what these graphs are, so a C3, you can draw it however you want. You can draw it like that, or note it's the same as this. And there's many other ways I guess you can draw it. And a P3, that's a, if you go back and look, a P3 is a subgraph, it's a path on 3 vertices. Path on 3 vertices. Okay, it isn't a path of length 3. Okay? All right, so let G be a graph of any graph of order 5 or more. Either G contains a P3 as a subgraph, or G complement contains a C3. Okay, and the result doesn't hold for 4. So let's start with the second part first. So I'm looking for what is the P3? G contains a P3 or G complement, G bar, contains a C3. So let me start with the previous step. Does the result hold for n equal to 4? So is there a graph on 4 vertices? So let's change this. Let G be a graph of order at least 4. In fact, forget the at least. Let G be a graph of order 4. For any graph of order 4, does it contain a P3 or the complement contain a C3? So can you give me a graph on 4 vertices? There aren't that many. Well, if it doesn't contain a P3, you almost know what the graph looks like. Okay, the graph does not contain a P3. So this graph doesn't contain a P3. And there's one more, this graph doesn't contain a P3. And that's it, all right? If we add any more red edges, we'll have a P3. P3, remember this is a P3. Okay, and if I add this second edge in any other way between these two pairs of 2 points, then I would have a P3. Okay, so the graph, it either looks like this or it looks like this. But we might as well assume that it has as many edges as possible. So what would we want in the complement? What do we want in the complement? Or what don't we want in the complement? A C3. So remember, the question is saying every graph of order 5 either contains a P3 or the complement contains a C3. So let's look at what is the complement. I'll draw it in blue, and I'll bring it over here. Does that contain a C3? What is it? What is a C3? Oh, I drew it. Does that contain a K3? Complete graph on 3. So 4 is not enough. Okay, so that's the second part of this. Does the result hold for n equal to 4? No. Okay, but one more. 5. 5, and they claim that the result works. When I say works, what is that? Let's see what that means. Okay, so I have a graph of order 5. And I want to show that it either contains a C3 or the complement contains a P3. Okay, so let's start. I mean, the easiest. Let's look at the graph, a graph that doesn't contain a P3. So, tell me what a graph that doesn't contain a P3 look like. Well, okay, so just to make it clear, this doesn't contain a P3. Okay? So let's start adding edges. That doesn't contain a P3. Can I add any more edges? Where? Okay. This doesn't contain a P3. Okay, so if I have a graph on 5 vertices, that doesn't contain a P3, can I add any more edges? This is it. That's it. If you have a graph on 5 vertices that doesn't contain a P3, it's either, this. It's either this, or, oh, what the heck. or this. Those are the only three possibilities. Those are the only three graphs on 5 vertices that don't contain a P3. So, I mean, look, if I can do it for the worst of these meaning the bottom one, if I can show that the complement has to contain a what? A C3. What is a C3? What is a C3? Just for the heck of it, I want to be sure that we know what a C3 is. So is there a C3 here? By the way, is there a C3 here? In the complement. Is there a C3 in the complement here? Is there a C3 in the complement here? Is there a C3 in the complement here? So what we've just shown is that either the graph contains a P3 or the complement contains a C3. And one more time, and that's not true on 4 vertices. Here is a graph on 4 vertices. Either the blue graph doesn't contain a C3 and the complement doesn't contain a P3, or the graph doesn't contain a P3 and the complement doesn't contain a C3. Okay, so you've shown that. Okay, questions? This is a fundamental part of a lot of graph theory. This idea of extremal problems like this. So now pick your favorite 2 graphs. Give me two graphs. Don't make them crazy.
K4.
K4 and
C3.
C3. By the way, C3 is K3. Okay, here's the question. What's the smallest graph so that smallest n, so that every graph on n vertices contains C3, or the complement contains K4. By the way, C3 is K4, K3. C3 and K3 are the same. Okay. So has anybody looked at that problem? I mean, this is a fundamental problem in graph theory. And in fact, you can change it to any 2 graphs you want. H and G. What is the smallest n so that every graph on n vertices contains H, or the complement contains G? And this was introduced by the Archbishop of Canterbury in 1928. And these are called Ramsey numbers. It was Archbishop Ramsey, but he had a different name. They give different names. Okay, questions? More questions about the homework? Was there another problem? Or was that it?
That's it.
That was it. Questions? Okay, so Stetson Zirkelbach will be here on, what's today? On Tuesday. Did I post a review sheet or something? Did I post something?
Yeah.
It's up? Okay, so basically it goes through a bunch of things that you should know the definition for. It gives you a few things you probably should know how to prove that the sum of the degrees is what? Twice the number of edges. You probably should have some good feel for bipartite graphs. We spent some time with bipartite graphs. You should know what trees are. You should know what, there's a lot of definitions that we went through. I'm gonna say, I think the test is pretty straightforward, but you never know. Okay? I will be available by email if you are desperate and want to talk to me. Otherwise, Have a nice weekend.
Test is on Tuesday?
Do what?
Thursday.
Oh, no. I could.
Okay, gotcha.
This one? No, so this one, C3 and K4? So here's a graph. Here's a graph that doesn't contain a C3, right? And its complement, the complement is, yeah, pretty far from complete, right? Wait, what is the complement? Do you want to hint?
What's the smallest one so that array, what?
Bigger. Bigger.
What is the smallest n so that every,
Uh-huh.
So for the relationship between degrees,
oh, so every graph on n vertices contains a C3
Yeah, the sun.
or a K,
What did he do?
Or the complement also, so that.
or the complement contains K4. I wrote it here, actually. Yeah, that was a little confusing.
Okay, so the min degree is right. Okay, so what's the, I think he read this as the degree of every point is the degree of any point plus the degree of any other point.
oh, not necessarily specific.
Right, yeah,
Okay.
okay. So if you look at this graph, if you look at the product, right, the degree of this point is the degree in here plus the degree in here.
Right. And
So
that's
this-
what I meant. I think I just didn't write it
Yeah,
correctly.
yeah.
Okay, got it.